The moment your boot touches the surface, nothing dramatic happens. And that's exactly what makes it unsettling. There's no sound except your own breathing inside the suit. No winds you can feel. No immediate signal from the universe that you've just done something extraordinary. And for a few seconds, it almost feels underwhelming, like the greatest leap in human history has been reduced to a quiet, weightless step onto dust that has been sitting undisturbed for billions of years. You look down, expecting something familiar, but the ground doesn't quite behave the way your instincts predict the way it would on Earth. Because the gravity here is weaker, subtly but unmistakably different. And your body notices, even if your mind hasn't caught up yet, you take another step, then another, adjusting without thinking. And as your eyes lift, the horizon pulls your attention outward, curving more tightly than it should. The sky above it tinted in a muted, almost artificial hue that never quite settles into a color you can name. And that's when the distance begins to register. Not as a number, not as 225 million kilometers, but as something far more immediate. Something you feel rather than calculate. Everything you have ever known. Every environment that shaped you, every invisible force that kept you alive without effort, is gone from here. Replaced by a world that does not recognize you, does not support you, does not care whether you function within it or not. And still, in that moment, there is a kind of quiet satisfaction. Because you made it. You crossed the boundary. You stood where no human body was ever supposed to stand. And for a brief stretch of time that feels like enough. But what you don't notice, what no one can feel as it begins, is that your body has already started responding. Not emotionally, not symbolically, but biologically, mechanically, with the same indifference that governs everything else in this place. The shift doesn't wait for you to settle in. It doesn't give you time to appreciate the achievement. It begins immediately, because the conditions that defined you for your entire existence have just been removed. And the body does not hesitate when its environment changes. Gravity here is weaker, significantly so. And that matters more than anything you can see. On Earth, every movement you've ever made, every step, every moment of standing still, has been shaped by a constant force pulling you downward, a force your bones resist, your muscles work against, your heart compensates for. Thousands of times a day without you ever needing to think about it. That constant demand is what keeps those systems intact. What tells your body they are necessary, worth maintaining, worth the energy they require. Remove that demand, even partially, and the body doesn't celebrate the relief. It reinterprets it as excess. So now, as you move across the surface, your bones are already beginning to adjust to a world that no longer requires their full strength. Your muscles are already receiving signals that their current capacity may be unnecessary. Your cardiovascular system is starting to recalibrate for a lighter load. All of it happening below the threshold of awareness. All of it proceeding with a kind of quiet efficiency that would be impressive if it weren't working against you. You don't feel weaker. Not yet. Because this isn't a sudden failure. It's a gradual redefinition. A slow drift away from the conditions that once defined what your body was built to do. And the real problem isn't that this is happening. It's how long it will continue. Because getting here already took months. Months of living in an environment that began this process long before you ever saw the surface. Months of letting your body adapt to something that was never meant to be permanent. And now that you've arrived, that adaptation doesn't stop. It deepens. It compounds. It becomes more difficult to reverse with every passing day. By the time a return even becomes possible, the version of you that left Earth may already be too far removed to survive going back. That realization doesn't arrive all at once. It builds quietly, just like the changes happening inside you, until it settles into something you can't quite ignore, a recognition that what you're experiencing isn't just distance, it's separation at a level far deeper than location. You didn't simply travel across space. You stepped into a different set of conditions, and your body is already choosing which version of you it needs to become to survive here. You're not standing on Mars as a visitor. If you ask most people what makes a return from Mars so difficult, they'll start listing things that sound reasonable: fuel requirements, launch windows, the complexity of landing and taking off from another planet, the sheer distance involved, and none of those answers are wrong. But they all miss the point in a very fundamental way, because every one of those problems, at least in principle, has a technical pathway forward, something you can engineer around, optimize, improve, or eventually solve with enough time and resources. That's how we got here in the first place. Rockets used to be impossible. Then they were dangerous. Then they were rare. And now they are, if not routine, at least repeatable. Technology moves in that direction. It bends, adapts, it scales, but your body doesn't. And that's the part that changes the entire equation. Because unlike machines, the human body is not designed to be reconfigured for entirely different environments on short time scales. It is the product of a very long, very specific history, shaped over billions of years under one set of conditions that have remained remarkably stable compared to the rest of the universe. One gravity, one atmospheric pressure, one magnetic shield, every system inside you: bone, muscles, blood, heart, brain, has been calibrated not just generally for a planet, but precisely for this one. Earth isn't just where you came from. It's what you are built for. And when you remove that context, the body doesn't pause and ask what your mission objectives are. It doesn't care about timelines or ambitions or the symbolic importance of stepping on to another world. It responds to inputs, always, relentlessly. If the inputs change, the body changes, not because something has gone wrong, but because from its perspective, everything is working exactly as it should. Take gravity, for example, not as an abstract force, but as a constant pressure your body has been negotiating with since the moment you were born. Every time you stand, your skeleton is under load. Your muscles are engaged. Your heart is pushing blood upward against that force. Your entire physiology is quietly maintaining a balance that you never notice because it has never been absent. Remove that force, or even reduce it significantly, and the body doesn't interpret it as freedom. It interprets it as a new baseline. Less load means less need for support. Less resistance means less need for strength. And once that signal is established, the body begins to adjust accordingly. Not slowly in evolutionary terms, but surprisingly quickly on human timescales. This is what makes the problem so difficult, because you're not fighting against a malfunction. You're fighting against an adaptation. Every loss of bone density, every reduction in muscle mass, every cardiovascular adjustment is the body becoming more efficient for the environment it currently occupies. From a biological standpoint, that's success. From a mission standpoint, especially one that requires returning to Earth, It's a slow-moving failure that cannot simply be reversed by turning a system back on. You can build a stronger spacecraft. You can carry more fuel. You can calculate trajectories with extraordinary precision. None of that changes the fact that the human organism inside that spacecraft is continuously recalibrating itself in response to conditions that drift further and further away from those on Earth. And the longer that exposure lasts, the more those changes accumulate, layering on top of each other until they form a new equilibrium, one that is stable in space or on Mars, but incompatible with life back home. What makes this even more unsettling is that the process is largely invisible while it's happening. There is no single moment where the body crosses a clearly defined threshold and stops being Earth-ready. Instead, it's a continuum, a gradual shift where each day seems manageable. Each change seems minor, until enough of them have compounded that the gap between what your body is and what Earth requires becomes too large to bridge. And by then, the problem is no longer theoretical, no longer something you can solve with better engineering or more planning. It is written into your physiology, into the structure of your bones, the strength of your heart, the way your blood moves through your body. The obstacle was never out there, waiting in the distance between planets. Let's make this concrete, because up to now it might still feel abstract, like we're talking about general adaptation without really seeing what that means inside your body. And the truth is, it's far more specific, far more physical, and far less forgiving than most people realize. The moment you leave Earth's gravity behind, not metaphorically, but literally, the environment that has been applying constant mechanical stress to your body disappears. And with it goes the single most important signal your body uses to maintain its structure. On Earth, you are always under load, even when you think you're resting, because gravity never stops pulling on you. And your bones and muscles are constantly resisting that pull in ways so automatic you never notice them. That resistance is not optional. It is the reason those systems stay strong in the first place. Now remove it inside a spacecraft during those long months in transit. Your body floats. And that floating is not neutral. It is interpreted as a complete absence of demand. Your skeleton, which has spent your entire life supporting your weight, suddenly has nothing to support. And the cells responsible for maintaining bone density begin to shift their behavior. Bone is not a static material. It is living tissue, continuously broken down and rebuilt in response to stress. And when that stress disappears, the balance tips in one direction, formation slows, resorption accelerates, and the structure that once held you upright begins to thin from the inside out. Calcium, once locked into the rigid framework of your bone, is released into your bloodstream and eventually excreted. As if your body has decided that carrying that extra mass is no longer worth the cost. The rate of this change is what makes it alarming in microgravity. Bone density can decrease by 1 to 2% per month, which might not sound dramatic until you extend it across the duration of a Mars mission. 6 months in transit, and you could already be looking at a loss approaching 10% or more. A year, and the numbers climb further. By the time you reach the surface, your skeletal system has already been compromised in the very areas you depend on most when gravity returns: the hips, the spine, the femurs, the structures designed to bear weight that no longer exists in the same way. Muscles follow a parallel path, and in some ways, they respond even faster. Without gravity, your legs no longer need to push against the ground. Your back no longer needs to stabilize your posture. Your core no longer needs to maintain balance in the same constant way. The demand drops, and your body adapts by reducing what it considers excess. Muscle fibers shrink, strength declines, and even the composition of those fibers begins to change, shifting toward types that fatigue more quickly because long-term endurance is no longer required in a weightless environment. Astronauts on the International Space Station spend hours every day exercising with specialized equipment designed to simulate resistance. And even with that effort, the loss is only slowed, never fully prevented. And this is where the situation becomes more difficult to dismiss, because we already have data, not from theory, but from real missions. Astronauts who spend 6 months in low Earth orbit, still partially protected by Earth's environment, often return unable to stand without assistance. Their bodies, after just half a year, struggle to readjust to gravity they have known their entire lives. Recovery can take weeks, sometimes months, and in many cases, bone density never fully returns to its original baseline. That's after a relatively short mission with constant monitoring, immediate medical support, and the certainty of coming home. Now, extend that timeline, not 6 months, but years, not a short trip, but a sustained absence of the very force your body depends on to maintain itself. Each month adds another layer of change, another reduction in structural integrity, another step away from the conditions your physiology was built for. There is no sudden collapse, no single point where everything fails at once, just a steady, cumulative erosion that continues as long as the environment remains unchanged. Your body isn't breaking down in the way you might expect from damage or injury. It's optimizing for a world where strength is no longer required in the same way, where carrying dense bones and powerful muscles becomes inefficient. And the longer you remain in that environment, the more complete that optimization becomes, until the version of you that could once stand effortlessly under Earth's gravity exists only as a reference your body has quietly abandoned. There's a tendency to think of space as empty, as a kind of vast, silent vacuum where the primary danger is simply the absence of air or gravity. But that picture is incomplete in a way that matters more than most people realize. Because what fills that emptiness is not nothing. It's radiation, constant, penetrating, and fundamentally unavoidable once you leave the protective envelope of Earth. Down here, you are shielded without ever having to think about it, wrapped in a magnetic field that deflects charged particles and an atmosphere that absorbs much of what gets through, reducing your exposure to a level your body can manage over a lifetime. It's not zero, but it's controlled, predictable, something your biology has evolved alongside. Step beyond that shield, and the rules change immediately. In deep space, there is no magnetic field strong enough to protect you, no thick atmosphere to soften the impact, only a continuous potok of high-energy particles arriving from every direction, many of them originating from events so distant and so violent that their journey began long before you were born. Galactic cosmic rays, composed of protons and heavy ions, accelerated to significant fractions of the speed of light, do not behave like the radiation you might be familiar with from medical imaging or environmental exposure. They do not stop at the surface. They pass through spacecraft walls, through shielding, through your body, depositing energy along their path in ways that are both microscopic and deeply consequential. And the problem is not a single exposure, not one dramatic event you could point to and say, this is when the damage happened. It's accumulation. Every particle that passes through you has a chance to interact with your cells, to break chemical bonds, to damage DNA, to introduce small errors into the code that governs how those cells function and replicate. Your body is not defenseless against this. It has repair mechanisms, sophisticated ones, capable of identifying and correcting many forms of damage. But those systems evolved under Earth's radiation levels, not under the constant bombardment of deep space, and over time, the balance begins to shift. Errors that would normally be corrected start to slip through. Mutations accumulate, layer upon layer, each one insignificant on its own, but collectively pushing cells further away from their intended function. This is where cancer risk emerges, not as an immediate threat, but as a statistical inevitability over long enough exposure. The longer you remain outside Earth's protection, the higher that risk climbs, until it becomes less a question of if and more a question of when. But focusing only on cancer misses a more immediate concern, one that affects not just long-term survival, but your ability to function day to day. Radiation does not discriminate between cell types. It affects neurons just as it affects skin or bone. And recent research, particularly from animal studies exposed to simulated cosmic radiation, suggests that the brain is especially vulnerable in ways that are subtle but profound. Structural changes begin to appear, including the loss of dendritic spines, the tiny extensions that neurons use to communicate with one another. Fewer connections mean slower processing, reduced cognitive flexibility, impaired memory. Imagine trying to operate complex systems, make critical decisions, or respond to emergencies while your brain is gradually losing efficiency. Not suddenly, not dramatically, but just enough that reaction times stretch. Judgments become less precise, and the distinction between familiar and unfamiliar begins to blur. These are not conditions you would accept in any high-risk environment, and yet in deep space, they become part of the baseline. And unlike many engineering challenges, this is not a problem with a clean, scalable solution. You might think the answer is simple: add more shielding, make the spacecraft walls thicker, more robust, capable of blocking incoming radiation. But physics complicates that approach. High-energy particles interacting with dense shielding materials can produce secondary radiation, sometimes even more damaging than the original particles, creating a cascade effect that turns protection into a new source of risk. Every kilogram of additional shielding also demands more fuel, more energy, more structural support. And the rocket equation does not forgive excess mass easily. So you are left in a situation where complete protection is not currently achievable, where exposure is not optional, and where the damage is cumulative and irreversible. There is no moment when it stops, no threshold after which your body is safe again. Only a continuous process of interaction between high-energy particles and the biological systems that were never meant to endure them for extended periods. You won't feel it as it happens. No pain, no warning, no immediate signal that anything is wrong. And that's part of what makes it so difficult to grasp, because the absence of sensation creates the illusion of safety. Even as the underlying changes continue, one event at a time, building toward consequences that only become visible much later, when the accumulated damage has already reshaped what your body is capable of doing and what it can no longer sustain. If you trace the consequences of all of this a little further, beyond bones and muscles, beyond radiation and DNA, you arrive at something more unsettling, because now you're looking at the systems that keep everything else alive and coherent. the ones you rely on every second without ever thinking about them. And you begin to see that the changes are not isolated. They are systemic, layered, and deeply interconnected. Start with the heart, not as a symbol, but as a pump that has spent your entire life working against gravity, pushing blood upward through your body roughly 100,000 times a day, maintaining pressure, maintaining flow, maintaining a balance that only makes sense under Earth's conditions. In microgravity, that resistance disappears. And the body responds in the only way it knows how, by adapting to a reduced workload. Blood no longer pools in your lower body the way it does on Earth. It shifts upward, redistributing toward your chest and head, creating a condition that the body interprets as excess fluid. The response is efficient and immediate. Fluid is expelled. Blood volume decreases. And the cardiovascular system recalibrates to match this new, lighter demand. The heart itself begins to change, gradually losing mass as it no longer needs to generate the same force it once did, becoming a smaller pump for a system that now requires less from it. None of this feels catastrophic in the moment because the system remains functional within its new parameters. But those parameters are drifting further and further from what would be required back on Earth. And the problem reveals itself not while you are in space, but when you attempt to return to a gravitational environment that expects the original configuration. A heart that has adapted to reduced demand is suddenly required to perform at full capacity, to push blood upward against gravity with less muscle and less volume to work with. The result is instability, severe drops in blood pressure, dizziness, the inability to remain upright without fainting. This is not a minor inconvenience. It is a fundamental mismatch between what your body has become and what the environment demands of it. At the same time, another system is being quietly altered in ways that are far less intuitive. In microgravity, the upward shift of fluids increases pressure inside the skull, and that pressure has nowhere to go. It pushes against the back of the eye, gradually changing its shape, flattening structures that were never meant to be compressed in that way. The optic nerve can swell, the retina can distort, and vision begins to change, sometimes subtly, sometimes permanently. Astronauts returning from relatively short missions have reported needing corrective lenses they never required before. And in some cases, the changes do not fully reverse, extend that process over years instead of months. And you are no longer talking about inconvenience, you are talking about structural alterations that may not be correctable at all. Then there is the brain, the system that integrates everything else, that allows you to think, decide, react, and maintain a coherent sense of the world around you. You might expect it to be protected, isolated, resilient in ways other tissues are not, but the evidence suggests otherwise. The same radiation that damages DNA and other cells affects neurons, and the structural changes observed in experimental studies point to a gradual degradation of the connections that allow those neurons to communicate effectively. Dendritic spines, the tiny structures that form the basis of neural connectivity, can be reduced in number. And with that reduction comes a measurable decline in cognitive performance. This is not a sudden loss of function, not a dramatic moment where everything stops working, but a slow erosion of clarity. Memory becomes less reliable. Reaction times stretch. The ability to process complex information under pressure diminishes, and the subtle distinctions that guide decision-making begin to blur. In an environment where precision matters, where small errors can cascade into critical failures. Even a slight reduction in cognitive sharpness carries consequences far beyond what you would tolerate in everyday life. What makes all of this particularly difficult to confront is that each system continues to function within its adapted state. The heart still beats, the eyes still see, the brain still thinks, but all of them are doing so under conditions that are steadily diverging from those required for life on Earth. There is no single point of collapse, no moment where everything fails at once. Only a continuous progression where each system moves further from its original baseline, reinforcing the changes in the others. And taken together, these shifts form something more than a collection of individual problems. They become a new physiological state, one that is internally consistent, stable within its environment, and increasingly incompatible with the world you came from. As if your body is not breaking down, but reorganizing itself into something that belongs somewhere else. There's a moment, somewhere after the initial arrival, when the environment starts to feel almost manageable. And that's where the real misunderstanding begins. Because Mars does have gravity. Not the complete absence you experienced during transit, not the disorienting weightlessness that forced your body into rapid adjustment, but something in between. About 38% of what you knew on Earth. And at first that feels like a kind of relief. A partial return to normalcy. Your feet stay on the ground. Your movements regain a sense of direction. Objects have weight again, even if it's reduced. And for a while it's tempting to interpret that as stability, as if this intermediate state might be enough to hold your body in place, to stop the changes you know have already begun. But your body doesn't recognize partial in the way you might hope. It recognizes load, demande, and necessity. And on Mars, all three are still dramatically lower than what shaped you. Every step you take requires less force. Every movement engages less resistance. Every moment spent standing places far less stress on the structures that once defined your physical limits. To your perception, it feels easier. To your body, it feels unnecessary. And that distinction matters more than anything else, because the same processes that began in microgravity do not reverse here. They simply continue at a different pace. Your bones, already weakened from months in transit, do not suddenly rebuild themselves because some gravity is returned. The signal they receive is still one of reduced demand, and so the balance remains tilted toward loss, perhaps slower, perhaps less dramatic, but still moving in the same direction. The dense architecture that once supported your full Earth weight continues to thin, continuing to shed what it no longer needs to carry. Muscles follow, adjusting to the lighter load, maintaining only what is required to function in this new environment, not what would be required somewhere else. The cardiovascular system, already recalibrated, continues to operate within a framework that assumes less resistance, less effort, less strain. And this is where the timeline becomes critical, because Mars is not a brief stop, not a short mission where you endure the environment and then return before it has time to reshape you. The mission profile demands time, long stretches of it, waiting for orbital mechanics to align, living in this reduced gravity not for days or weeks, but for many months, often well over a year. Every one of those days reinforces the same signals, the same adaptations, the same gradual drift away from the conditions your body was built for, What makes this particularly deceptive is that you can function here. You can walk, work, operate equipment, perform tasks, even feel at times, capable and adjusted, because within this environment, your body is doing exactly what it needs to do to keep you alive and effective. There is no immediate sense of failure, no obvious indication that something critical is being lost, because the loss is defined relative to Earth, not to Mars. Within this world, you are becoming well adapted. That is the problem. Because adaptation is not neutral, it is directional. Every adjustment your body makes is a step toward compatibility with this environment, and at the same time, a step away from compatibility with the one you left behind. The longer you remain, the more complete that transition becomes, until the gap is no longer something that can be closed with recovery time or rehabilitation. It becomes structural, encoded in the density of your bones, the strength of your muscles, the behavior of your cardiovascular system, and then, after all of that, comes the return journey, another long stretch in near zero gravity, compounding everything that has already occurred, stripping away even more of what remains, reinforcing the adaptations that Mars began to solidify. By the time you approach Earth again, the body you inhabit has spent years under conditions that bear only a partial resemblance to the ones waiting for it below. This is where the idea of a point of no return stops being metaphorical and becomes physiological. Not a single instant you can identify, but a threshold you pass gradually, quietly, without any clear signal that it has been crossed, until the accumulation of changes reaches a level that cannot be undone within any reasonable time frame. At that point, returning is no longer a question of trajectory or fuel or mission planning. It becomes a question of whether the body that adapted so well to survive out there can still survive where it began. And the answer is no longer guaranteed. By the time you put all of this together, not as isolated facts, but as a continuous process unfolding across years, the conclusion stops feeling speculative and starts feeling almost unavoidable. Because every part of the journey, from departure to transit to life on Mars and the attempt to return, pushes in the same direction. It is not one failure point, not one catastrophic limitation, but a convergence of changes, each reinforcing the others, each narrowing the space in which a safe return remains possible. And what makes it difficult to accept is that none of these changes are dramatic in isolation. None of them arrive with a clear warning that says this is where you should stop. This is where you should turn back. Because by the time such a warning would be meaningful, the process is already too far along. You leave Earth with a body perfectly tuned to one environment, one gravity, one set of conditions that have shaped every aspect of your physiology, and from the moment you depart, that tuning begins to drift. Months in microgravity initiate the process, reducing bone density, weakening muscles, altering the cardiovascular system, exposing you to radiation that accumulates quietly within your cells. Then you arrive on Mars, where gravity returns but only partially, not enough to restore what has been lost, only enough to slow the decline while reinforcing a new equilibrium, one that is internally stable but increasingly incompatible with the demands of Earth. You live there, not briefly, but long enough for those changes to deepen, to become embedded, to define a new baseline for what your body considers normal. And when the time comes to leave, to attempt the return that was always part of the plan, you carry all of that with you. The journey back does not reverse the process. It extends it, adding more time in reduced or absent gravity, more exposure, more adaptation, until the version of you that approaches Earth is no longer the same as the one that left it. The difference is not just measurable, it is functional. It determines what you can withstand, what you can survive, what your body is capable of doing under conditions it has not experienced for years. This is where the idea of a round-trip mission begins to unravel. Not because we cannot calculate the trajectory or build the vehicle, but because the human system inside that vehicle is no longer compatible with the destination it is returning to. Bones that have lost significant density may not support full weight. Muscles adapted to a lighter environment may fail under normal gravitational load. A heart that has recalibrated to reduced resistance may struggle to maintain blood pressure when gravity demands more from it. These are not edge cases, not unlikely scenarios, but direct extensions of what we already observe over much shorter missions. So the framing changes. What was once described as exploration begins to look more like relocation. Not in a symbolic sense, but in a biological one. The first humans to reach Mars may not be temporary visitors at all, even if that was the intention, because the cost of returning is written not in fuel requirements or mission budgets, but in the cumulative transformation of their bodies. The longer they stay, the more complete the transformation becomes, until leaving is no longer simply difficult, but fundamentally incompatible with survival. And this is where the conversation shifts from engineering to acceptance. Because if the constraints are set by biology, then the decision must be made before the journey even begins. To go to Mars under these conditions is to accept that the ground you step onto may be the ground you never leave. Not because of failure, but because success itself carries consequences that cannot be undone. It is a different kind of commitment, one that extends beyond the mission timeline into the structure of your own body, into the irreversible ways it will adapt to a world that is not the one you came from. The first humans on Mars will not just represent a technological achievement or a milestone in exploration. They will represent a transition, the moment when human presence in another world stops being temporary and becomes permanent. Not by design, but by necessity. Because in reaching further than our bodies were built to go, we may find that the only way forward is to let go of the place that made us what we are.